Welcome back to Math 104. Why is it true that each entry in row n equals the sum of the two entries directly above it in row n minus 1? For example, why does this 21 in row 7 equal the sum of the 15 and the 6 above it right here in row 6? Well, the 21 words that have 5 R's and 2 L's, that's what this 21 is counting. The 21 words with 5 R's and 2 L's come from two sources, because the 21 paths that reach this location in the hexagonal grid come from two sources. The words are formed by either taking one of these 6 words with 5 R's and 1 L, and then tacking on an L to the end. That's like paths that have gone right 5 times and left once, and then go left in the final step. Or words that live here could come from one of the 15 words that have 4 R's and 2 L's, and tacking on an R to the end. Those correspond to the 15 paths down to this location, which currently have 4 rights and 2 lefts, and if you just go right one more time, you'll land in this location. Since every 7-letter word with 5 R's and 2 L's arises in one or the other of those two ways, but never both, the total number of such 7-letter words equals that sum. We've already seen row 7 and how it gets used in some probability computations. Let's look at another example, now involving a family with 8 children. As soon as you see that now we're talking about families with 8 children, the first thing you should do is write down row 8 of Pascal's triangle, because row 8 of Pascal's triangle knows about this experiment in the same way that row 7 knew about the experiment with 7 children. So we apply our rule. We begin with a 1, and then we sum 1 plus 7 equals 8, 7 plus 21 equals 28, then we get 56, 70, 56, 28, 8, and 1. After we've found all the numbers going up to the middle, we'll then just get a mirror image of them on the other side. So a family with 8 children is selected at random. Let's find the probability that at least one child is a boy. A useful thing to do in problems like this is to mark up which items in row 8 of Pascal's triangle contribute to this event. Now, depending on whether you think of this as 0 girls, 1 girl, 2 girl, 3 girls, etc., all the way up to 7 girls, in which case these are all the outcomes that have at least one boy. Or if you think of it the other way, as 0 boys, 1 boy, 2 boys, 3 boys, etc. up to 7 boys, in which case you'd put the box around everything except for the initial one. Either way, the numbers inside this red box count up how many outcomes are in the event that at least one child is a boy. The easiest way to think about it is as 1 minus the probability of the complementary event, 0 boys, which is 1 minus 1 over 256. Where did I get 256 from? Because 2 to the 8 is the total number of distinct possible outcomes in the experiment. Thus, 1 over 256 is the probability of no boys at all. 1 minus the probability of 0 boys equals the probability of at least one boy. So that is 255 divided by 256. To answer the next question, let's create another copy of row 8 of Pascal's triangle, so that we can mark it up separately. Let's think of this row in terms of increasing numbers of girls. In other words, this one corresponds to words with 0 G's and 8 B's. This 28 corresponds to 2 G's and 6 B's. This 8 over here corresponds to 7 G's and only 1 B. Now notice that in order for an outcome to be in our event here, at least one child has to be a boy, which means that this outcome is excluded. This is 8 girls and no boys. Furthermore, there have to be at least 2 girls. In other words, we have to be looking at this 28 or something to the right of this 28. Because of this and here, we need to satisfy both of these constraints, and therefore it's the numbers inside this box that are counting up outcomes in the event. The remaining 1 plus 8 plus 1, which is 10 outcomes, are the outcomes that don't live inside our event. Now we could sum the numbers that are inside the red box and divide by 256. Or we could take 1 minus the probability of the complementary event. And that has probability 10 over 256. and therefore our event has probability 246 over 256. If we flip a fair coin 8 times, what is the probability of obtaining exactly half heads and half tails? To practice our notation, let's understand that the probability we're looking for here can be written as 8 choose 4 divided by 2 to the 8th. 2 to the 8th because there are 2 to the 8th different possible outcomes for the experiment, and 8 choose 4 because this is counting how many, and then why 8 choose 4, because there are 8 stages to the experiment, and we're interested in 4 of them being heads, and the other 4 being tails. We need to know the number in row 8, entry 4, where we start counting from 0. 0, 1, 2, 3, 4. 8 choose 4 means the number in the middle of row 8. So that is 70 over 256, which is approximately 0.2734. Keep this in mind because you're about to compare it to the answer to essentially the same question about 10 coin flips. It was at the beginning of the course that we first asked about the probability that on 10 flips of a fair coin, we would obtain exactly half heads and half tails. Before going on to the next video, answer the following questions. If we flip a fair coin 10 times, what is the probability of obtaining exactly half heads and half tails? Think of what information you'll need in order to answer that question. And then, how does your answer compare to what we just found for the same question with only 8 flips?